Hi everyone, this is the Genuinely Approachable Sudoku for October 16th, 2023, entitled Procrastination, set by Philip Newman. That's me. If you are watching this, in all likelihood you are coming from the CTC Community Discord and the Daily Sudoku Puzzles channel, and you already know what I'm about to say about this. But if you're not coming from there, when I posted this, in the intro, I mentioned that I had set it with the intention of recording a video and including it with the puzzle. And my goal with that was I've been thinking about doing some kind of short Sudoku theory videos, talking about some technique or some variant or some interesting project that I've been working on or whatever. My thinking was, if I'm going to do that, I need to start from the basics, even though this has been done before, just so I can start with a good foundation and talk about some things that inform how I look at Sudoku. And that might be important down the road when I'm talking about some more advanced things. So, this puzzle, since it's a genuinely approachable Sudoku, it's intended to be solved by anyone who understands the rules of Sudoku and who's willing to put in a little time and effort. It doesn't have any super tricky steps that you can't figure out just from the rules. I'm going to talk about what those not so tricky steps are and how you can find them more easily, and how they are derived from the rules. Because our goal here is to solve this puzzle logically. We don't want to guess. So, let's start with the rules. Normal Sudoku rules apply. What does that mean? It means in each row, and in each column, and in each 3x3 box, we must place the digits from 1 to 9 exactly once each. And each cell must contain exactly one digit. That last part is often unstated, but it is an important rule, especially in the world of variant Sudoku where that may not be true. When we say each row, column, and box must contain each digit from 1 to 9 exactly once each, that's kind of hiding two pieces of information. And the first is each row, column, and box must contain every digit at least once. And the second bit is each row, column, and box must contain every digit at most once. So for the first part, if we haven't placed a digit in a box, and if it's not a given digit, we need one somewhere. So if we haven't placed 1 in box 1, we know we still have to place 1. And if we ever get to a point where we can only place 1 in one cell of box 1, then it has to go there. Otherwise, we don't have anywhere to put it. So that's called a hidden single. A hidden single is when you have a digit that can only go in one place in a row, column, or box. The second part leads us to naked singles. So a naked single is a cell, say this cell, that can only contain one digit. It's the opposite of a hidden single. And the reason we can end up with naked singles is because each digit can appear at most once in each row, column, and box. So this 3, for example, there's already a 3 in the column. There can't be a 3 here, or we would have 2 3s. So we can rule out 3 from this cell. If we can do that for all but one of the digits, then that last digit has to go there, and we can place it. Otherwise, the cell doesn't have anything that it can contain, and we only have 8 cells to place 9 digits. That's not going to work. Now, in this video, we're mostly going to talk about hidden singles. We will get a little bit into naked singles sort of later in the solve. In my experience, most of the techniques that you're going to use in any Sudoku are hidden singles. You will also use naked singles at some point in most puzzles. And then depending on how hard it is, you'll use some other stuff. But in order to place digits, for the most part, you have to use singles. There are a few exceptions to that, but beyond the scope of this video. So we're going to look at these two types of singles, and more specifically, we're going to look at patterns that emerge in puzzles that can lead you to look for them. So the first one we're going to start with is probably the first place you should look in any classic. And that is if you have a band is 3 boxes sharing 3 rows. 3 boxes side by side, however you want to phrase that. Or a stack, which is 3 boxes stacked on top of one another. 3 boxes sharing columns. If you have a band or a stack and you already have 2 of the same digit, you should probably look at where it can go in the 3rd box. And you won't always be able to place that digit, but sometimes you will. And even if you can't, you'll be able to narrow it down. So we're going to start with 1. And 1 is already in row 1. And since 1 is already in row 1, that means we can rule 1 out of all of these cells. 1 is already in row 3, which means we can rule 1 out of all of these cells in row 3. If 1 were in any of the gray cells, we would have 2 1s in a row. And that would break the rule. Now, in this case, in box 1, we have these gray cells, but we also have 2 given digits that are not 1. We can't put a 1 in those cells either. We couldn't anyway because of these ones, but we don't even need them in this case. We can't put a 1 with a 4. So the only place for 1 in this box is right there. Now, there are multiple ways you could see that. You could look at the columns as well. This one means 1 can't go in these cells. This one means 1 can't go in these cells. This is a 2, this is a 7. So 1 goes there. You could even just look at the 1s. This one rules out these cells, this one rules out these cells, this one rules out these cells, and this one rules out these cells. Let's go to box 3 now. If we just looked at these, we can rule 3 out of those cells and that cell. We have to look at the other 3 here. We can look at both of them if we want. But 3 is eliminated from all of these cells in box 3. 3 can only go here. So anytime you have 4 of a digit looking at the same box, you're going to be able to place that digit in that box. Same is true for 7 here. We have 4 7s looking into box 7. This is the only place for 7. 9. We have 4 9s. We could also just look at the band. This is the only place for 9. And in box 5, we have 4 5s. That's the only place for 5. So that's a very common pattern. Maybe not always at the beginning of puzzles, but definitely as the puzzle progresses, you will start to see that. And sometimes it's helpful to highlight all of a particular digit. You can see those patterns more easily. Okay, so now we're going to look at box 1 again, and we've got 5 digits already. So there's a couple of different things you could do here. We're going to focus on the singles, but it would be totally reasonable at this point. I should say we're going to focus on the hidden singles. It would be totally reasonable at this point to say, okay, I have 4 cells left. What 4 digits do I need? I need 5, 6, 8, and 9. Okay, well, these two can't be 8. These two can't be 6. Oh, I have a 5 here and a 5 here. Okay, so 5 has to go there. This is something to look out for where you have 4 cells that are empty and they make a square or a rectangle like this. This cross shape of givens and filled values. You could have a T, you could have a L or a V. But anytime you have this shape of empty cells, it's worth looking for common digits looking into that box. Because this time we only need 2 givens to make a placement. 5 can't go in those cells, and these are already filled. So this has to be 5. Now that we have that 5, we can look down here and place 5. We can look down here and place 5. And we can look up here and place 5. And we have all the 5s. So this would be the second sort of pattern that you'll see a lot. Instead of 2 digits in the same band, you have 1 digit in the band and 1 digit in the stack looking at the same box, and that can give you a placement. So again, that's a hidden single in the box. This, just to go back to this 5, this is a hidden single in the box. These 5s rule out 5 from the rest of their columns, and we have givens there, so this is a hidden single in the box. But I'll point out it is also a hidden single in the column. 5 can't go in these cells. This 5 rules out these cells in the same box. Can't have 2 5s in box 4, and then these are givens, so this is 5. So again, there are multiple ways of seeing the same deduction. It's pretty common to have a hidden single in a box and a column at the same time, or a box and a row, or even all 3. We can look at 4 now. So 4 in this stack already appears in this box and this box. So we're looking at this box. We've eliminated 4 from this column. We have 2 givens. That's a 4. 6 on the right, and these 2 givens means this is a 6. So the next placement is similar to the 5s here. We're going to use 1 5 in the band and 1 5 in the stack. It's a little different in the pattern, and the pattern here is in box 4. Now that we've placed this 4 here, we have filled all of the cells in this column in box 4. So that means we don't have to worry about where 9 is up here, basically. We know 9 can't appear in these 3 cells without knowing where 9 actually is in this column. We have a 9 here, we have a 9 here, and this is a given. So this is the only place for 9. So anytime you have 3 cells filled in the same row or column in a box, and up here when we had our little cross, we had both the row and the column in box 1. But anytime you have that, it's worth looking for digits that don't share that column that can look into that box. Likewise, this 9 is ruled out of these, and it can't appear here, so it's up here somewhere in this column. We can do the same with 1 in box 6. These can't be 1, this can't be 1, that can't be 1. back down here in box 7, we've got 3 here. Can't go in those cells, or those cells, or those cells. So that's 3. In box 3, we have 7. Can't go in those, or those, or those. Now we only have 2 cells left in column 3, and you can see this as a hidden single or a naked single, either way. The digits we have left are 2 and 6. This is a 2, so this cell sees 1, 2, 3, 4, 5, 7, 8, 9. Which means this cell has to be a 6. The other way to look at it as a hidden single is this cell can't be 2. There's nowhere else for 2 in the column. This is a 2. So either way you see that, this is a 2, this is a 6. And in this column, this can't be 8, so this is 8 and this is 4. And depending on how you solve and just how your brain works, you might see that first as this is the only place for 8, or you might see that as this can only be 4. It really doesn't matter, and it seems to depend on the person. I wouldn't say either is any faster or slower necessarily. Now, we could get all of this with hidden singles. Probably the next thing you're going to look at is going to give you some naked singles. So I'm going to go ahead and talk about that, but I'm going to come back to look at some other hidden singles that are a little harder to spot. And that's why you're probably going to see the naked single first. So in these boxes, we now have 6 digits. And same for the column. And anytime you have a pattern like this, these 6 digits are going to be the same as the digits in the column, because these 3 are the missing ones. So these 3 digits are 3, 6, and 8. And we have a 3 and an 8 here. So the only thing this can be is 6. That's a naked single. These 3 digits, we need a 2, 4, and 7. And we have a 2, 7 here. This has to be a 4. You may be used to a lot of pencil marking. I am deliberately avoiding pencil marking anything in this puzzle because I'm going to talk about those pencil marks in a future video. But also just to point out, you don't necessarily need to solve with pencil marks, and sometimes it can be faster to not. I notice a lot of times when I am solving, especially when I'm test solving gas, I will see these 3 cells need to be 3, 6, 8, and I'll go ahead and type them before noticing, oh, there's a 3 and 8 there. I should put a 6. Now I have to remove 6, and I've kind of wasted some time doing that. Now, if you're not solving for speed, it doesn't matter. But even when you're not solving for speed, relying too much on pencil marks can be a little confusing. You can end up with too many. So in this solve, I'm going to deliberately not use them, but in the next video, I intend to. So, all right. So I mentioned there were some hidden singles at this point, because we could pencil mark these cells, we could pencil mark these, we could pencil mark these. There's lots of stuff we could pencil mark, but we need to find a placement. So we're going to look at column 4. And probably this is not the place you would expect to look. And it's not obvious why you should look at column 4. So I'm not going to suggest that you should. I'm going to suggest instead you should be looking at where all the 9s are. And you'll see we have 6 9s already. We don't have one in column 1. And we don't have one in column 5. And we don't have one in column 4. Now, where can the one in column 4 be? It can't be here because of this 9. And it can't be here or here because of these 9s. And it can't be down here because of this 9 or these other 9s. So in fact, there's only one place for 9 in this column, and it's right here. So that's a hidden single 9 in column 4 that probably you're going to see by looking at the 9s, not by looking at the column. We can do the same with 1 in column 6. This puzzle is totally symmetric, but let's highlight the 1s. And where does 1 go in column 6? Can't go in these cells, can't go here or here, can't go here. These are not 1. This is our 1. What about 4? 4 can't go here or here or here or here. It only has one place left in the column now too. That wasn't the case before we placed the 9, but placing the 9 as a hidden single now gives us a hidden single 4. Placing the 1 in this column means 6 can't go in any of these cells, so 6 goes here. Now in this row, we need to place a 7. There's a 7 here, so this is our 7, this is our 8. We need 2 and 3 in this row, 2, 3, from this 3. The rest of this column can view this as a hidden or naked single, I think. Where does 2 go? Can't go here, can't go here because of that 2. So that has to go here. You could also look at it as, what is this cell? It's not 1, 2, 3, 4, 5, 7, 8, 9. It's a 6. So 6 there, 2 there, and our last digit is 3. In this column we have 4, 7, 8. This can't be 7 or 8, it's 4. This is the only place for 8, and this must be 7. And now in this box, this can't be 4, so 4 goes there. This is 6. One digit left here. This is 8. And this actually has another name. It's actually a hidden and a naked single at the same time on the same digit. This is called a full house. So if your house, your row column, or your box is almost full, you can fill it. This needs to be a 2. This is the last digit in the box or the column. It's a 7. This is a 3. Now we're getting to the end, and this is another common pattern you'll have at the end of puzzles sometimes. You have 2 possibilities in each box, and some other digit in the row is going to disambiguate them. So this is 8 or 9. We can't disambiguate that because there's no 8, 9 here. But here we have 2 or 9, and there's a 2 here. So this is 9, this is 2. And now that we have the 9, that's the only place for 9, that's 8. That's got to be 4, that's got to be 8. Down here, we need 1 and 8, and we have an 8 there. 1, 8. This is the last place for 1. This is 2. This is 6, and this is 2. And that's the solution. And that time is from when I was solving it earlier. So I hope that was a little bit helpful in how you might approach finding singles. There are lots of different ways you can look at Sudoku puzzles. You can try highlighting a particular digit. You can try pencil marking everything that you need that's left and eliminating stuff. But these patterns of given digits appearing multiple times in a band, or having 3 cells filled in the same column of a box, and looking at other digits like we did here, they pop up over and over and over again. And really understanding hidden singles and naked singles, even if you don't call them that, doesn't really matter what you call them. Understanding how you place digits is going to inform how you approach the puzzle and how you approach more complicated techniques. So that's all I have on solving. I'm going to switch my view now to setting. And I want to talk about how I set this puzzle in the first place. So my idea for this puzzle was to give each digit as a hidden single in its own box. So we had at the start of the puzzle 4 ones, all looking at box 1. So from the start of the puzzle, we could place a 1, even if we didn't have any digits in box 1. The same was true of 3 in box 3, 5 in box 5, 7 in box 7, and 9 in box 9. It wasn't the case with the even digits, but originally when I set the puzzle, that was the intention. I typically set puzzles using F-puzzles. This was software originally created by Eric Fox, and Ranksk has done a lot of work integrating his solver into F-puzzles. At this point, I believe Afraid Not has taken over the domain, and they're working on some new features. But currently, what I use for most of my setting is F-puzzles with Rank's solver. And so it may look a little different than if you're just used to F-puzzles without those extra scripts. But I have some cells highlighted. Those cells are just the pattern of digits that I wanted. So I realized very quickly, if I'm going to have ones looking into box 1, I think they were here and here, something like that. I've already forgotten where they were. I need 4 ones, right? But if I'm going to have that on every digit, I'm going to end up with 4 digits in each box. And the reason for that is, let's consider box 1. Box 1 sees box 2 and box 3 and box 4 and box 7. So if I want 4 digits looking into box 2 to place a 2, one of them has to go in box 1. I have to have a 2 in box 1. And if I want 4 threes looking into box 3, I have to have a 3 in box 1. And same with 4, and same with 7. So to achieve that goal, that original goal, I have to have 2, 3, 4, 7 somewhere in this box. Now, I decided I would try to have them in this pattern like this. And I was hoping to do something like this. I've done this sort of thing for some other variants. It doesn't actually work. If you try to force these cells, it breaks. It doesn't have any solutions. But what I did is place pencil marks in those cells. So I know that I want a 2, 3, 4, 7 up here, and I know I want them in these cells. I know I want 2, 4, 6, 8. These, since I knew I couldn't get all 4 where I wanted them, I limited it to 3 cells. And then we're going to see where the 4th digit can go. So I turned on True Candidates. And what True Candidates does is tell me, given these restrictions, given I have these pencil marks, what digits can go where. And eventually, there we go. I had to tinker with it a little bit. So eventually it will show us this. And in particular, you'll note this cell if these are limited to 1, 3, 5, 8, and all these other restrictions are here, this cell can only be 7 or 9. We can't put the fourth digit there. And in fact, these 3 cells are only from 1, 3, 5. So that's kind of interesting. So really the only decision to be made now is, where does 8 go in this box? And where does 6 go in this box? And where does 4 go in this box? And where does 2 go in this box? So what I decided was to make these triples, because that usually leads to some pretty simple logic. So we're going to make this an 8. We're going to make this an 8. We're going to make this a 6. We're going to make this a 2. And we're going to make this a 4. And now the true candidates are telling us that these digits are forced. This isn't necessarily something we can get logically, but it is true. In fact, if I turn on the logical candidates, all those red digits means, for example, this can't be a 6, but proving that it can't be a 6 is not just singles. It might be tuples. Yeah, it is tuples. So we can place these with pairs and stuff. So now the question was, can I make this unique by actually fixing where these digits go? And so I decided to do this the simplest way I could. I'm just going to put these digits in order. And I'm just going to put these digits in order. And I'm going to put these digits in order. And I'm going to put these digits in order. And as I put more digits, it's getting more and more forced. You'll notice if I put a 1 here, this green means it's unique now. That's the only solution. But that's not an orange cell. That's not part of my pattern. So I noticed this orange cell, this 1 is kind of faint. That means it has fewer solutions. So that seemed like a good candidate. And in fact, that makes it so that the 9 is making it unique. Okay, so that's basically how I set this puzzle. I had a concept for it. I used the solver to see how many solutions it had, see what restrictions there were, and then place digits. So in this box, the digits are in order, but counterclockwise. So 1, 4, 8, 9. In this box, it's clockwise, 1, 2, 6, 9. Counterclockwise again. No, not counterclockwise. Bottom to top, left to right, I guess. Anyway, I filled all of these in. And this was my original puzzle. And this is a perfectly fine puzzle. It's very easy. Significantly easier than what I actually ended up with for gas. I decided it wasn't quite interesting enough. So I started removing digits. And the first ones I removed probably obviously were the ones that weren't part of my original pattern. So it's still unique. In fact, if I can turn on logical candidates, it still solves with singles. So then I thought, what else can I remove? Well, maybe I can remove all of these. And we have to remove the center marks as well to make sure that it's still unique. I think I tried removing some other things like this 1 maybe, and it's not unique anymore. So that doesn't work. Probably there is something else we can remove. Maybe not. Maybe the 7. Yeah, the 7 and the 3. The 2 we can remove, and the 8, and it's still unique, but now it's harder. So now we need tuples to solve it, which means we need pairs or something similar. But I decided I liked my corner boxes the way they were and just stuck with that original pattern, just removing box 5. So it made the solve a little more interesting. Now, this isn't how I set every puzzle I set. It's not how I set every gas, certainly. For variants, usually we're trying to bring out some of the basic logic for that variant. So we will definitely start with, okay, I'm going to put a killer cage, these sum to 3. Well, that has to be 1, 2. Go from there. And it tends to be much more placing one thing at a time and seeing where that leads. But sometimes you have an idea for a puzzle and you end up throwing a bunch of constraints at it and making it unique and then hoping it solves nicely. So that's kind of what I did with this puzzle. So I hope that's interesting. Let me know if you want me to talk more about my setting process. It's a little hard to do because I don't record while I'm setting usually, and probably 99% of the time that wouldn't be very interesting for me to do anyway. I'm just tinkering, but I can definitely talk more about how I set puzzles if that's interesting. Also, if you have any suggestions for this series, what things you would be interested in me talking about, I have some ideas. There's probably 30 things on my list of topics that I could do videos on. Some of those topics may be of interest to a very small number of people, so I don't want to get too obscure, at least early on. So definitely open to feedback and your thoughts about this video. But thank you for watching.